Welcome to my video course on railway safety and systems engineering. I'm absolutely thrilled to have you here today as we unpack the critical pillars that keep modern mass transit moving. You know, if you've ever stopped to wonder what actually guarantees that a multi-ton train rocketing down the tracks won't just collide with another, or why a seemingly tiny track issue can bring a massive rail network to a grinding halt, well, the answer comes down to a really delicate, highly engineered balancing act. Today, we're focusing squarely on three massive concepts that dictate literally every aspect of railway operations: safety, reliability, and availability.
In this specific explainer, we're going to break down the mechanics of mass transit systems by looking at the exact metrics engineers use to guarantee performance. We're stripping away all the heavy jargon to look at what actually happens in the real world when these systems face extreme pressure, harsh weather, and just the chaotic, unpredictable nature of daily operations.
Okay, let's dive into this. Here's our roadmap for today. First, defining the ram's core. Second, examples in railway operations. And finally, the ram's relationship. Section 1, defining the ram's core.
So in systems engineering, you'll often hear the acronym RAMS. That stands for reliability, availability, maintainability, and safety. Today, we're zeroing in on the big three, starting with reliability. By definition, this is the probability that an item will deliver its required function when required. In plain terms, it's just answering one simple question: will this equipment actually work when we need it during service? We usually measure this using MTBF, or mean time between failures. Let's put that into perspective. If you have a population of 120 items on your railway and you get 50 failures in a given year, your average MTBF for an individual item is 120 divided by 50. That gives you 2.4 years. A highly reliable system is going to gracefully handle power blips, self-diagnose its own internal faults, and just plain not break down very often.
Next up, we have availability. Now, this is defined as the proportion of time for which the item is in a state to perform its required function. Think of it as uptime divided by total time. While reliability asks, will it break? Availability asks, for how much of the time is this system actually usable? It's all about continuity of service. And in railway systems, any unplanned availability that drops even a hair below 100%, that causes immediate delays, a big loss of revenue, and some seriously unhappy customers. And finally, we get to safety. The strict definition here is freedom from unacceptable risk of harm. When we're talking about the rail environment, safety is generally split into two really vital categories. First, you've got system safety. That's all about protecting train movements at all times, preventing collisions, derailments, and making sure crystal clear instructions are given to the drivers. Second, there's staff safety. That means guaranteeing that the folks out there operating, maintaining, or installing these control systems are never exposed to danger. And this brilliantly illustrates a common trap a lot of people fall into: conflating reliability and availability. Listen, they are not the same thing. You can absolutely have a piece of equipment that's highly reliable, meaning it almost never breaks. But if it does break, and it takes incredibly long to find the replacement parts or to safely get out on the track to repair it, your availability just plummets. Your mean time to repair, or MTTR, directly drags down your availability. High reliability doesn't automatically guarantee high availability if your repair processes take a massive amount of time. Section 2, examples in railway operations. Now, what's really interesting about this slide is how interlocking systems perfectly demonstrate the fail-safe principle in action. Think of them as the brains of railway safety. They ensure a signal is only cleared if the route ahead is proven safe, and there are zero conflicting paths set. Modern interlockings actually have to meet Safety Integrity Level 4, or SIL 4, which is the highest requirement possible. They achieve this massive safety integrity by strictly adhering to fail-safe principles. If a hardware or software fault pops up within the interlocking, the system is hardwired to fail in a way that immediately puts all signals to danger, stopping all trains. It defaults to the absolute safest possible state. Another classic example you'll recognize is the level crossing. When engineers look at risk reduction, we use a hierarchy of controls. The absolute best option? Elimination. Just remove the crossing entirely. The next best is substitution, like building a bridge over the tracks. But when those just aren't feasible, we have to rely on engineering controls to physically separate the hazard from the people. Level crossings use some incredibly sophisticated train detection engineering to trigger lights, barriers, and those loud audible alarms. These mechanisms act as a vital engineering control to keep road users safely separated from a massive, fast-approaching train. But here's the catch.
Keeping these engineering controls reliable is incredibly tough because the physical rail environment is just brutal. Poor reliability often stems from severe external conditions. For instance, track circuits, which are there to detect the presence of a train, they can fail if the track ballast gets flooded or contaminated. That causes the system to think a track is occupied when it's actually completely clear. You've got unstable tracks at switch points that can cause intermittent loss of detection. Plus, all these sophisticated electronics are constantly bombarded by vibration, wild temperature swings, and electromagnetic interference. The environment itself constantly threatens the system's ability to just function reliably.
Section 3, the RAM's relationship. Let's move to and see how this builds into what we call the cascade effect of failure. It's a 4-step chain reaction. Step 1, poor reliability causes an interlocking or a track circuit to fail. Step 2, because that equipment has safely failed, trains are stopped dead and system availability drops to 0. Step 3, well, the railway still has to keep moving, right? So signal operators are forced to resort to manual, degraded mode workarounds to authorize trains to pass red signals. And that leads to step 4. Because human beings are now manually managing these train movements instead of the computers, the safety risk dramatically spikes due to the potential for human error.
So, the crucial point is this. Failing equipment literally strips away the automatic protections that prevent catastrophic collisions. A highly reliable system is a safe system, mostly because it keeps operators from having to improvise. When a system breaks, those manual procedures are just inherently less safe. They override fail-safe designs. They rely on verbal communication, which, let's face it, is highly susceptible to human error. They remove automated protective boundaries, and they place intense, massive pressure on signal operators to manually manage a really complex spatial puzzle in real time.
I want to leave you with this provocative thought to summarize the core, interconnected tension between reliability, availability, and human safety. If an engineering system is perfectly fail-safe, meaning every single time it glitches, it successfully turns all signals red, but it's so poorly maintained that it's constantly breaking down, is it truly a safe system? Because if it breaks down every single day, operators are going to be forced to manually bypass those safety systems every single day, which introduces massive risk. True safety requires high reliability.
I hope this has fundamentally shifted how you view the incredible engineering behind railway control systems. We've covered a lot of ground today on the fascinating interplay of RAMs. Thanks, we can see you in next video.